Stars are thought to be born in the dark patches of nebulae like this gas lane known as the Cone Nebula. These cool, dark clouds are moving slowly, so the gravitational attraction between particles can overcome their random movements and produce a contraction of the cloud. As the gas cloud contracts under the force of gravity, the compression raises the temperature of the core until it reaches several million degrees Celsius. At this temperature, nuclear reactions begin, and a star is born. The mass of the resulting star determines its surface temperature, size, and color. Like a metal bar that's heated until it glows, hotter stars are successively red, yellow, white, and finally distinctly bluish at very high temperatures. Blue stars produce enormous amounts of energy. The source of energy that makes stars shine is a nuclear reaction involving the conversion of mass to energy. That this is possible was first realized by Albert Einstein and is expressed in the equation E equals mc squared. This indicates that a small amount of mass, m, can be converted into a large amount of energy, E. C is a constant, the speed of light. The reactions within a star involve the fusing together of atomic nuclei. The basic nuclear fusion reaction is the conversion of 4 hydrogen atoms into 1 helium atom. And this conversion involves the loss of a small amount of mass as a large amount of energy. An average-sized star, like the Sun, will keep on fusing hydrogen into helium for around 10 billion years. More massive stars burn up their fuel more quickly and have shorter lives. Small stars live even longer than the Sun. When the hydrogen in a star's core is exhausted, a period of instability begins, which signals the beginning of the end of a star's life. When a star can no longer burn hydrogen, it'll begin to build heavier elements by fusing helium atoms together. All these reactions take place at much higher temperatures at the core of a star. These higher temperatures make the star expand to many times its original size. The outer regions of such a star become cooler as they get further from the core, so the surface temperature drops and the star turns red. The result is a red giant, a very large and bright star. This is the red giant star Betelgeuse, which is about 750 million kilometers across, or 2.5 times the diameter of the Earth's orbit around the Sun. Betelgeuse is one of the largest stars known. Red giants will usually go through periods of instability in which the outward pressure will throw material into space. This star is steadily losing material from its outer layers. The materials formed a small nebula around the star. The Helix Nebula is a fine example of what are called planetary nebulae, because they resemble planets when seen through telescopes. The helix consists of a number of spherical shells that have been thrown off a star during a period of instability. This is another star that's vigorously ejected its outer layers to produce a series of shells, including a symmetrical pair that were probably produced in the same outburst. After such a star has lost some of its mass and exhausted its nuclear fuel, it'll collapse to form a white dwarf, a very dense star not much larger than the Earth. A white dwarf is so dense that a tablespoon of its matter would weigh a ton. It can appear white or even blue because its surface is very hot due to the energy created in its collapse. The evolutionary pattern of stars that we've been looking at applies mainly to those of medium mass, like our Sun. Stars of much greater mass might come to a more dramatic end, as a supernova, an enormous explosion in which much of the star is blown away into space. A supernova will leave in its wake an outwardly expanding shell of material. This web of gas covering a large area of sky is known as the Vela supernova remnant. One of the best-known supernova remnants is the Crab Nebula, the result of a supernova in 1054 AD that was recorded by the Chinese. At its center, astronomers discovered a strong source of radio waves pulsing in a very regular way. Many objects like this have been found. They're known as pulsars. Pulsars are thought to be rapidly rotating neutron stars, stellar remnants with strong magnetic fields. Particles moving within these fields produce powerful radio waves along the lines of the magnetic axis. As the star rotates, this radio signal is like the moving beam from a lighthouse. Each time the beam points towards us, we see a pulse. Neutron stars, although usually heavier than the Sun, are only about 10 kilometers in diameter, making them incredibly dense. A tablespoon of matter would weigh 10 million tons. They're called neutron stars because it's only the force between neutrons that prevents their further gravitational collapse. With a star of greater mass, there is no force which can prevent total collapse, and it'll become a black hole. A black hole is so small and dense that nothing at all can escape from its surface, not even light. It can, however, be detected by the radiation emitted from matter spiraling into the hole, such as from a companion star in a double system. Black holes are often thought of in terms of Einstein's general theory of relativity. This drawing represents a black hole as a hole in the fabric of space. The large distortion or warping of space is due to the enormous gravitational field of a black hole. Black holes play a significant part in many theories about the nature and history of the universe.